Welcome back to this episode. Now we're gonna see the practical part. So if you haven't seen the first part, it's the theory part. So I introduced the concepts for microcontrollers, what they are, what's the difference between a microcontroller and a microprocessor. So if you haven't yet watched, please do. Now we are ready to get practical. By the end of the video, you will learn how to cross-compile programs to build for ARM microcontrollers with CMake, set up your own ARM microcontroller development container in VS Code, writing a basic C++ program that is testable, object-oriented, debugging in VS Code, and finally testing your own program with mocked interfaces. In case you don't have your physical hardware with you, but you still want to test your software. You learn how to do that today. Alright, so I've prepared for today's video a repository. This repository is dedicated to highlight the main topics, and I want to make a big disclaimer here. This is not a standard way to approach a microcontroller project. Usually we use a vendor supplied IDE or we use another set of tools to build application. But I really want us to rediscover, to walk through the process of building a full-fledged microcontroller application. So for today's video, we will be using our usual tools that I use for all the past videos also, CMake, dev containers. And I really want to go to the same process and the same thought process, even if I want to build application for a complete different architecture. All right, so if the very first thing I usually look into project is the dev container. So let's do a small recap. Dev containers are dedicated containers that hosts and have already pre-built toolings for building your applications. In this particular case, I've prepared a dev container that already has a lot of C++ tools that I reuse all the time. So I don't need to specify a Docker file containing all the things I want to install that allows me to build my application. I actually made one, and this is its name, and I already posted this in Docker Hub. So all I have to do to build C++ application, generic applications, is to pull this image as a dev container and install basic extensions. So if I do Command-Shift-P and I do rebuild container without cache, the only thing it's doing is fetching this image again and make sure that the image is downloaded and it runs. So right now, if I open my terminal, I am inside a container, and this container that I prepared contains every tool set that I will need to build a C++ application. So it has GCC, it has G++, it has also the ARM compiler to cross-compile on my application to the microcontroller. So it's a pre-built dev container that has all the tooling that I need to get started with C++. Plus, I also put some extra libraries that I very often use in my hobby projects, like Point Cloud Processing Library and other stuff like gRPC. So I made a dev container that has a lot of stuff that just it facilitates and speeds up my development for a C++ application. If you want to know more about this, I'll post the link in the description with the link to the Docker Hub of this image, and you can see all the steps and all the run commands that installs all the needed applications. Now, jumping on to CMakelists. So this is the tool to go to describe my build process for C or C++ application, and it's very important for this video purpose that we use the same thing to build our C or C++ application for the microcontrollers. This is how the file looks like. This is quite usual, and those are the first two things to think about. So if we're cross-compiling applications, usually we produce different artifacts on our native laptop host architecture, let's put it like this. And for ARM architectures, those are the executables that it understands. So right at the beginning, I state that, hey, I create those two variables, and those two variables will contain the actual name of the binaries that I will, in the end of the day, putting in the flash memory of this device, and it will load it, and it's going to run the program that I'm building right now. So keep that in mind. That I create these variables so that I use them later on. This is quite usual. It's just a CMake formatting process. So my code gets automatically formatted This is often how I do it. This is to include all directories in every target that I build. This makes sure they all see those header files. And now comes the important part. Let's skip this for now. If we are cross-compiling, then we build the following lines. Quite easy to understand, right? But what does it mean actually? So CMake as a build tool allows us to cross-compile. This means that CMake knows that whatever I am building for a different architecture than my laptop that I'm using to record this video. How does it do that? So there's a thing in CMake, in VS Code, it is even easier to set this up. There's something called kit. And the kit is basically a collection of compiler or build tools. And specifically within this .dev container, there's a number of those compilers. So here we can see already, hey, if I want to compile for ARM architecture 64 bits, which is the laptop's architecture, I just select this. If I want to build for microcontrollers, I use this one. And CMake automatically knows that, hey, if I am not building for my host architecture, then execute those lines in the build system. So this is to make sure we are actually building a application targeted to a different architecture, which is our microcontroller. For the particular case of this project, I made my own kit tool set. This is part of the dev container. So this kit, I made it specifically for today's video. And the reason it's different than this one that is automatically found by CMake is that this one sets one or two flags that makes the build system really work well. So it's not a big difference. All right. So just to be clear, we are targeting our application to build for ARM microcontrollers, and this is how I called it, ARM. And this will trigger our CMake to run all those lines below here. Very important to understand. This is how we do cross compilation. And there's a good reason also I put this outside of CMake cross compiling flag. I'll tell more in a bit. Perfect. Moving on, I first set a variable called HAL. HAL stands for Hardware Abstraction Layer. For STM32 microcontrollers, the supplier provides us with this HAL layer already. So this means that I can program my peripherals. Remember what the peripherals are? They are a way to interface with external things. So the supplier allows us to use a higher level language or a higher level API to communicate with those building blocks, such that my application that uses them doesn't really care about lower level stuff. As my application is probably gonna need this HAL, I'm gonna build something on top of the HAL, I want to build them also. And a very important thing about the support story is that all the supplier libraries or dependencies that really builds all the lower level foundations are included as a submodule. So I added them in this HAL subdirectory right here. And another disclaimer, a quick disclaimer, is that whenever we buy a microcontroller that belongs to a certain family or a supplier, they will give you a very nice IDE that abstracts this thinking away from you. So it's going to be much easier if you use your supplier tool to develop your application, because they already know, hey, I'm going to use this startup script, I'm going to use the HAL, I'm going to use this include header. The reason I'm not doing exactly like the supplier is saying is exactly to rediscover the steps. Okay, what is exactly happening behind the curtains if I use a supplier given tool? And here we see exactly, oh, so this is what they do. They pick up the files, they bundle them together, and they build the application on top of the HAL, and they use this common standard CMSIS to build basic higher level foundations for your application. So I'm gonna put a picture right here on all the layers, and we are doing this same thing by hand, just because this is what happens behind the curtains, and I think this is important for us to know. So now that we know, we depend on those files. By definition, they build the foundation for application. For example, let's have a look at this startup this file. So Command P, I can type the file and it's gonna direct me to this. So this belongs to a library called CMSIS, which stands for Common Microcontroller Software Interface Standard. This is basically a common layer on application that is shared among all the different microcontrollers that belongs to ARM architecture. At least most of them. And there are versions of it. There are CM65, CMSIS6, and this is one of them. And the purpose of this CMSIS is that it gives us startup scripts, it gives us memory layout, it gives us really low-level things that we don't want to think too much, and they give us so we can already use. This is the startup script. It's the very first thing that runs in the microcontroller, and there is also this one, which is a C file that defines yet again more entry point level functions that it's going to be called, for example, systemnit. It's going to set up clocks for us. It's going to tell, hey, the microcontroller just woken up from the power cycle. Okay, what do I do? So it has very initial steps, very basic ones that we must do before we can run our application. Like I said at the beginning of the video, microcontrollers are quite straightforward, quite simple devices, but they do require some setting up. It's not like I can turn it on and suddenly I can load the program. It's not like this. You have to set up the registers. You have to look at some bits. There's a certain sequence. You have to set interrupts. So there's quite a curve, quite a sequence we have to respect. And after that is done, then we can run an application. Because it really doesn't know what to do at the beginning. We have to tell it. It's not like a CPU or like an operating system. We have to tell it what to do. And thus, CMSIS library makes our life much easier. Perfect. Now we know that we need this to build our microcontroller application. We create the library out of those files. We call it this, and just so you know, this microcontroller right here, it belongs to that family. So F1XX, this is the description. If you ask me how did I find this out, so you can literally Google Blue Pill STM32, it will tell you the family of microcontrollers. And the way CMSIS work is that you set up those files, and those files are organized per family. There is a small thing about the density, the chip density or the chip complexity of the chip, which is this code right here. And again, if we look at the microcontroller description, so there's a chip right here, there's a name. If you open that file information, the datasheet, it will tell you, hey, this is the density, this is the family, and then from that I could find that those files were needed. This is abstracted away if we use a supplied provided tool. So I'm just walking the same steps, figure out, hey, what is happening behind the code. Now we make a library that is our HAL. Those are the include folders, because whenever we need this library in our application, it's probably going to need the include folders to refer to the functions. And this is how we specify in CMake. This library is the set of these files plus those include folders. Now a very important step is the compilation flags. I know it might look way too specific, right? So there's a bunch of, where did I got those from? I actually got those also from the supplied toolchain. So the supplier sets up those automatically for us. When we build a native application, we often don't care about the flags because the compiler knows a lot about our system. It knows our architecture, it knows who it's compiling for, it knows the memory layout, it knows the architecture, set of instructions for our CPU. It knows a lot already because the compiler was built for your own laptop, for example. The laptop is aware. So there is all self-awareness happening there. Whereas if we build for microcontrollers, it's clueless. It doesn't know the architecture. It doesn't know. This is why it's called ARM non-EABI. It doesn't know anything. It has no assumptions. It's a very generic compiler. So we have to tell it, hey, this is the architecture. This is the instruction set. Do not use standard libs like printf, because what is the output? There's no output. So we have to be manual and specify, oh, there is a floating point or not. It's a software, so it's a simulator, so floating point. So we have to be manually setting those flags. So the compiler builds a code that actually runs our device. I think it's so cool to see that only thing we're doing with using compiler and setting flags and setting specified set of C or startup files, and that's pretty much it. It's cool to see that this is part of our artifact, of our binary. And it's cool to see the process of how a compiler that doesn't know anything about the chip actually ends up making the thing that works using those flags. And of course, CMake has a very nice function that allows us to connect those flags to our application. So whenever we build those applications, we set the same flags, and we also have to set this flag right here. It's actually a compile definition that then CMSIS is aware of the brand of microcontrollers. And finally, we also set linker flags. If you don't know what a linker is, the linker, it looks at every object that the compiler produced. So the compiler produced artifacts, let's say intermediate files, object files, and the linker brings all of them together into your final executable. The linker is the one that is aware of what your function you're calling is the actual code that was compiled in one of the C files. So the linker job is to figure out the naming also of the functions. And it's not it's also the case that the linker must be specified with specific flags, also compatible with the flags of the compiler. So some of them are actually coming from here. Finally, we have the compile flags, we have the linker flags. We are finally able to produce our executable. It's very same instruction as if we were building for our Linux or Mac OS or native architecture laptop. We just say what it's going to produce. So this elf out is coming from this definition. So we're going to produce an elf file, and we're going to link it as if we would link a usual C or C++ application. And we're going to make a new target that is invoking an ARM object copy that's going to produce this bin file. So elf file is the artifact coming out of this instruction, but we can further optimize it and make it an executable. This is full of instruction symbols or debug symbols, and this is really stripped away. It's quite clean. This is very much like we really want to flash the target with. Perfect. And of course, it depends on the elf. So first we go this, and then we do this. If we're not cross-compiling, so if else from this if, we build tests. And this is an important part of this video. The test frameworks, and I have a video about those for G-test, for example. We don't want to test our application in our microcontroller. We often want to test behavior. How is our system behaving? So the way we can abstract away is by being able to reuse part of the same code that you're building for your ARM microcontroller. What if we can use the same code, the same modules, to build a library or something that you would want to test in your native, in your host architecture? And this is what this is doing. This library is built regardless if it's a ARM architecture or a host architecture, regardless of its cross-compile. I'm going to produce this library. And if we're building for my native laptop, it's going to end up also here in the test subdirectory. If we go to the test subdirectory, we're going to see that our module or test executable depends on the applib. And this applib, which I call module, is a class. It's just something that works in either my test executable or my microcontroller executable. And this is the principle that we want to use if we want to make a testable application that works in a microcontroller in our host architecture, because it has to be buildable regardless of your target. So to be more clear, we have a module or a library that I build using this. If I use a ARM62 chip, I build the lib app. And if I set my kit to build for ARM, I also build applib right here. So I build the same thing for two different architectures, so I can run tests in my host architecture, and this can be part of a pipeline, for example, that tests the functionality of this class, and it's also part of my main executable that will end up running in my microcontrollers, like this one. So this is testable. This is a testable design. I can test this class, I can test this module, that works either way. And I want to really stress the importance of this decoupled architecture. I have a module that is testable and I can prove that. And finally, the main application. I'm sure some of you just want to get to that part. I'm very sure. Let's see how it looks. So this is the main executable. This is part of this artifact. This is the entry point of my application. A lot of stuff happens before that with all the startup CMSIS and HAL libraries, but it is quite quickly, very quickly, it ends up here. So for STM32 devices, usually it's provided this HAL coming from the libraries that we download externally by the supplier, and this is how it works. So if I want to use the HAL, the hardware abstraction layer, which is this very nice API that can call the peripherals, I have to do this, the HAL init. And if I want to use the delay function of the HAL, so there is a function called HAL delay. Let me see a implementation of this timing. So this function here will delay my application. It's like a sleep in a C, standard C or C++, and this will delay my application. This will hold my processor for executing anything for a specified number of milliseconds. It's quite convenient. So I just had to do this at the beginning, and then it works. So my application is quite straightforward, and you can already see that I'm using C++, and I'm going for C++. I'm also using C++ memory smart pointers construct. I like a lot the concept, the idea that I can make of object-oriented application out of a microcontroller, but I also want to disclaim that for very professional use, very professional applications, people often want to optimize their application to the highest possible level. So it's not very common in high-end applications and high-performance requirements to see C++ being the de facto language to use for microcontrollers. It's quite often that they're going to use C to really squeeze the performance out of the microcontrollers and not to leave out chances to the compiler to do silly stuff with constructors or destructors or memory allocation. So just to be clear, the way I'm doing right now is it may work for serious applications, but it's not often the case that this is used. But for the purpose of learning and showing that we can actually do this, we can actually program our microcontroller like this one in C++, a high-level language, and we can use smart pointers and we can use memory heap allocations. I think it's really cool, just the fact that we can use that and it works. Okay, enough talks, let's go see stuff happening. Now, in order to download this software into your microcontroller, you need a programmer. This is ST-Link V2. This is a programmer/debugger. This is used to effectively transfer your application to the physical device. And it's gonna do this in the flash memory of the device, so it's kept over pi cycles. But more importantly, it also allows you to debug your application. So you can also step your functions, step your variables, read your variables one by one if you want to. So it's quite handy equipment. It is also very cheap. So I have this one connected physically with my microcontroller right now. So if you see these wires right here, those are the physical connections to my debugger or programmer. However, you might be wondering, hey, this whole thing, this whole development environment is running inside a Docker container. How am I supposed to connect physically with a physical device? There's no connection, there's no abstract, there's nothing between. Thankfully, there is an extension called Cortex Debugger, or should I say Cortex Debug. This thing here allows our VS Code environment to connect remotely with the server of the ST-Link V2 application, which is really, really cool. So this means that if I have a server, something that is physically connected to my device, and it is online, so you start the server, I can simply point my Docker environment to that server, and everything works out of the box. I can establish a connection, I can flash my memory, I can start a debugger, and everything works. The way we do this is by using VS Code launch tasks, like this one, specifically this one. This tells the following. So given that executable, this is just a name we have, try to connect to the host Docker internal IP address over port 4242. And this is enough to tell VS Code whenever we try to launch an application to, instead of trying to run it natively, it's gonna try to run over the connection. And okay, so we have a client, we have ways to connect to the server, but where's the server? So you do need to download ST-Link tools. So for Mac, this is more or less like this. So this is a package. This is something you can download. Also for Linux, it's quite straightforward, for Windows as well. But you do need to have your host machine like this one. So this is my Mac terminal. You do need to establish the connection as a server to the ST-Link debugger or programmer. Thankfully, it's quite straightforward. So I just connected it to my USB in the MacBook. And all I need to do is do this, st-util. This starts the server and also tells the port. It tells what is the device, how much memory it has in the RAM, how much flash memory it has. So I have a connection to my device. It identified my device. Now we are ready to flash this application in our microcontroller. To do that, we simply have to run our application, and VS Code will trigger the launch task and make it work. So real quick, if you notice the blinking pattern is once a second. I'm gonna make it 10 times faster. And I'll just run without debugging. You can see here that is flashing my microcontroller. It's already finished. And then I have to hit the button stop to disconnect. And if we switch back to the camera, I hope you can see it, but it's blinking much more faster. So I'm gonna just revert the change. I'm gonna revert the change back to 1 second delay. This is the change, but I'm gonna flash it while looking at this camera. Flashing right now, you see the LED starts blinking. I'm gonna trigger the stop. There we have it. It's once more 1 second delays. Now we just saw how to program. The server is still up. I'll just leave this by the side, and let's see how it works with the debugger. So to debug, all you have to do, once you set this up, of course, so this serves both for debugging and flashing, all you have to do is go to run and start debugging. Notice that this is chosen as the option, debug with ST-Link util. And there's a very important thing here. I have to build my application with the debug flags on. And luckily for CMake, there is already a pre-configuration for that called debug, of course. And once I build, see how fast it builds. The memory usage is a bit higher, but now I should be able to start debugging my application. And there we have it. I just put a breakpoint in my dev container, remotely debugging my STM32 microcontroller. I think that's really cool. So right here, I'm gonna step over these functions, but I'm gonna prepare, let me just fix the windows. All right, so if I simply step by step, I can step even over the time that the LED turns on. It's already on, so nothing special. The delays, look at how easy it is to debug the microcontroller like this. I can see my letter turning off right now, it's off, and now I'm back into while loop. Turning on, and so on. It's quite cool, right? And if you want to flash it, all I have to do is run without debugging, finish the connection, and then my whole new application is working again. I think that's really cool. Finally, let's talk about testability. So, the question is, how do I test parts of my module, parts of my program, without having to rely on the microcontroller being present? I don't want to all the time flash my microcontroller to be able to test functionality. How do I do that? So the way we do this, one of the ways we do this is of course through abstraction. For example, imagine you have a module. This is something that has a certain behavior. It's part of the biggest part of your application. You want to test this. I want this to be testable. But I don't want to all the time rely on physical devices. I don't want to rely on connecting to my hardware and needing them to see an LED blinking on and off. Here comes the magic. We use object-oriented programming, passing interfaces like this. So we don't pass physical representations of our hardware, we pass virtual representations of this hardware to my module, to the thing I want to test. So it would work regardless if it's a physical thing or a virtual or a mocked thing. Here's the magic. I could pass mocks, I could pass simulators, I could pass anything that simply realizes the interface. And this is what I'm doing right now. For the purpose of using the object, real objects, this is what I do. I create pointers, I realize my interface. So this is a concrete implementation of the LED, which physically uses the HAL to turn LEDs on and off. The same goes to the UART. So the UART is using physical HAL transmissions and connections to my peripherals, and the same goes for the timing. In this example, I'm actually gonna flash my microcontroller. You're gonna see everything is working fine. This module is quite simple. All it does is blink the LED for a second or the specified time and sends a message over the UART wire. So I just flashed the memory and I'm gonna press the stop button. So the program is downloaded. And here we see a blinking LED pattern that I just programmed. So this extra wire that I put right here, it's actually sending UART information over a FTDI device, and the FTDI device transmit it through my USB-C device of my MacBook. So this is actually the message that I'm getting via wire physically. Sounds maybe too complicated, but if you think a little bit more on this, it's not too hard. Okay, now let's talk about how do I test this. I don't have a microcontroller with myself. I want to test this module. What do I do? Going back to CMakelists, we see the thing I want to test. This is my application module. It's the important critical part of my software. The rest is basically hardware abstractions. So I ideally would not need to use this to test my code. And right here, if it's not cross-compiling, it's gonna build this other part of my CMakelists, which is just the testing part. So I include ctest, so I can call the testing via VS Code and ctest application. And I add the subdirectory, and this is quite simple, quite straightforward. I use the Google test that is already part of my dev container. I add a test, include the Google test mock libraries, and we can build it. How to switch, you might be asking. So again, Command-Shift-P. I can use kit, you can just type kit. Now I want to build not for ARM, I want to build for my host machine compiler, which is Arch64. This one would work as well, but this one is just fine. So let's use this one. Oops, I selected wrong. Kit. I want this one. Okay, now I just set the build target, all doesn't matter, and I want to build. So here I am building with the native compiler, and I'm building the target test module. So actually this is what was just built. So you see, by the way, every auto-completion works just fine using Clang-D as a language server. It's a really nice one. And here I can test my module. So let me put a breakpoint right here. I'm going to switch to launch not via this one anymore, instead via this one, which is the GDB debugger, default debugger. And look at this, I can actually use the exact same module that I built for my microcontroller. That's the important part. But now I can pass mocked interfaces. I invoke my module and I can state my expects. So this module is supposed to do something with this mocked interfaces. And whatever it is supposed to do, I can already verify this at this level, unit testing. If I want to test the function blink, it's gonna turn the LED on, turn the LED off, and it's gonna do 2 delay calls. And the same goes for message. Of course, if I make this wrong and I run it without debugging, it is gonna fail the test because it expects that whatever I write here is gonna be sent to the mock UART. That is very important. That is a very important concept, that the way you develop your code, try to inject interfaces, try to use abstractions, try to get away from the dependency of hardware. This will help you drastically verify your code, verify your application, verify behavior, and it's of course easy to test. You can put this in a pipeline, you can put it in your CI/CD pipeline so that every time you do a new change in your codes, it's already verified. And try to keep it simple in the physical device. Let me switch back to ARM, restart language server to reload this. Yeah, every smart pointer works. I can build again for cross compilation, and the rest is just low level things. So this is how quickly it is to switch between building for your microcontroller and building for your host machine so you can test your application. And that concludes the video. I really hope you learned something new. So I can imagine this is quite a dense topic. There are so much that I didn't really cover, right? So what is the point of those functions? What is the point of this sysdig handler? What do I do with this and that? There is a very special thing in this kind of compilation for microcontrollers, for example, that requires you to specify a linker script. What is this linker script? What does it do? How do I use heap memory in my application? How do I specify the lengths and the sizes? Can I use heap memory even? So I'm aware there could be many questions regarding how to approach, how to be serious and professional developing microcontroller applications. But fear not, this information will come. What's important here today is that you realize that you can program microcontrollers, you can use dev containers, you can use remote debuggers, you can debug your application, you can test your application. And that, to me, is more critical than those small details to make the compilation work. In any case, the repository will be posted. I hope you can just literally clone this, run your dev container, and be quickly able to flash your STM32 device. And the idea is that it's really supposed to be simple. That's it for today's video. Once more, I hope you have learned something new. Keep tuned.